All right, today we are going to break down one of the most powerful ideas ever dreamed up by the human mind, calculus. Now, don't click away, I promise this isn't going to be some scary math lesson. Instead, think of it as the incredible story of a brilliant idea that lets us understand our world, a world that's always in motion, all by focusing on one single tiny point in time. So, let's get into it.
So let me start with a question that seems super simple, but is actually kind of impossible. How fast are you moving right now? I don't mean your average speed over the last minute. I mean your speed at this very instant. It's a total mind bender, right? And it turns out the normal math we all learned in school completely falls apart when we try to answer it.
And here's why. You know, calculating your average speed is easy peasy. It's just distance divided by time. But to find your speed at a single instant, well, the amount of time that has passed is 0. And what happens when you try to divide by 0? It's the one thing you can't do in math. It just doesn't work. The direct path is a total dead end.
And this is where the genius of calculus comes into play. If we can't figure out the answer head-on, we're going to sneak up on it. Instead of trying to deal with an interval of 0 seconds, we're going to see what happens when we make that time interval smaller and smaller and impossibly close to 0.
Okay, so let's try this out. Imagine we've dropped a ball, and we're tracking its speed. We're going to zoom way, way in on one specific moment and see what the numbers tell us. So check this out. Over a full second, the average speed is 24.5 meters per second. Fine. But look what happens when we shrink our window. At a tenth of a second, the speed is 29. At a hundredth, it's 29.45. At a thousandth of a second, it's 29.495. You see the pattern here, right? We're not actually getting to 0, but the speed is clearly homing in on one very specific number. It's getting closer and closer and closer to 29.5. It's like it's being drawn in by a magnet. And this beautiful, elegant idea, this trick of getting arbitrarily close to an answer without having to do the impossible, like dividing by 0, this is the absolute heart of calculus. And it has a name. It's called a limit. Okay, so this is the formal definition, but what does it really mean? A limit is simply the value that a function is approaching as your input gets closer and closer to a certain number. It's the tool we were looking for. It's our clever workaround for that whole divide by 0 problem, and it lets us find that one precise number our speed was aiming for. All right, so we've found our magic ingredient, the limit. Now we can use that ingredient to build the machine that's going to solve our impossible speed problem, and honestly, so much more. And this is it. This is the machine. It's called the derivative. I know, that formula looks intimidating, but I promise it's just our sneaking up method written down. See that little h? That's our teeny tiny slice of time. And the stuff on top? That's just the tiny bit of distance the object traveled in that tiny bit of time. So the whole thing is still just distance over time. And that lim part at the front just asks, hey, what number are we getting closer to as our slice of time, h, shrinks down to basically nothing? So what does this awesome machine actually do for us? Well, it has two really cool interpretations. Geometrically, it tells you the exact steepness, the slope of a curve at one single point. And physically, it gives us the instantaneous rate of change. And that's it. That's the answer to our original question. It's the exact speed at a specific moment. And this is the absolute perfect way to think about it. If a function is the whole story of your road trip, the derivative is your speedometer. It tells you exactly how fast you're going at any given instant along the way. It's the ultimate tool for understanding change moment by moment. All right, I get what you might be thinking. Okay, that's a neat trick, but who cares about finding the steepness at one single point? Why is this such a big deal? That is a totally fair question. Well, for starters, it lets us find the exact highest and lowest points of pretty much any situation you can imagine. We're talking about maximizing a company's profit, or minimizing the cost of materials for a project, or finding the absolute peak of a rocket's flight. This is the key to optimization. And the logic behind it is actually really simple. Think about climbing a hill. As you're going up, the slope is positive, right? And when you're going down the other side, the slope is negative. So what's happening right at the very, very top of the hill? For just a split second, it's perfectly flat. The slope is 0. So by finding where the derivative equals 0, we can pinpoint the exact location of every peak and every valley. But finding the peaks is just the beginning. We can actually do the same trick again.
Just like the derivative tells us how our position is changing, we can find out how our slope is changing. This is called the second derivative, and it tells us all about the shape of the curve.
We can tell if a curve is bending upwards, kind of like a bowl ready to catch some water. We call that concave up. Or is it bending downwards, like an arch? We call that concave down. This tells us things like acceleration or the point of diminishing returns in a business. It's incredibly useful.
So when you put it all together, it's like having a superpower. The first derivative tells you if you're going uphill or downhill. The second derivative tells you if the road is curving up or curving down. With just those two tools, you can create a perfect map of any function's behavior.
And trust me, this is not just some abstract math concept. This is the language our world runs on. Engineers use it to build bridges that don't collapse. Economists use it to predict how markets will grow. Physicists use it to calculate the orbits of planets. Data scientists use it to make AI smarter. Even animators use it to make cartoon characters move realistically. It is everywhere.
So I'll leave you with this to think about. What's one thing in your own life that's always changing? It could be your mood, your bank account, your progress at the gym, anything. And what new things could you learn if you could actually understand its instantaneous rate of change? That's the power calculus gives us. Thanks for tuning in.